Welcome to Hired in IT. Our mission is simple: help you build the skills that employers actually want. Whether you're trying to land your first IT job, switch careers, earn a promotion, or increase your salary, we're here to help. Every video is thoroughly researched and designed to make complex IT topics easy to understand. If there's an IT topic you'd like us to cover, leave a comment below. We may turn your suggestion into our next video. Turning IT knowledge into career opportunities. A hospital deployed an AI model to flag lung nodules in CT scans. Weeks later, a radiologist spotted a nodule the model had overlooked, partially hidden by a rib, a scenario the training data barely covered. That's not an AI failure. It's an engineering failure. Throughout this chapter, we'll fix that with data augmentation, transfer learning, and realistic validation. By the end of this video, you'll be able to do 3 concrete things. 1. Train a custom object detector even when you have only 50 labeled images. 2. Pull structured data from invoices and forms with high accuracy. 3. Upload a video and programmatically extract transcripts, labels, and faces using Video Indexer. Let's talk real money. A healthcare system manually correcting invoice OCR errors, OCR, optical character recognition, automatically reads text from images, found that a custom model eliminated thousands of dollars in rework. A retailer missed critical restocking signals because their generic video API wasn't tuned for their store layout. An automotive supplier bled cash on undetected defects. In each case, a custom domain-specific vision model caught what generic AI missed. That's the difference between a general-purpose API and a model built for your actual world. Here's where beginners get tangled. Image classification assigns one label to the whole picture. For example, contains a nodule. Object localization draws a single bounding box. Object detection combines them. It classifies every object and draws a box for each. If you confuse detection with classification, you'll build the wrong pipeline. This distinction is the foundation of the AI 102 computer vision objectives. Before we test recall, let's actually learn what IOU is. Intersection over union compares the predicted bounding box with the ground truth, the correct bounding box annotated by a human. The intersection is the overlapping area, and the union is the total area covered by both boxes together. IOU is the intersection divided by the union. Most benchmarks consider a detection correct when the IOU is at least 0.5. For high-precision tasks, you may raise that threshold, but 0.5 is the standard. Time to lock in the core metric. If you had to calculate it right now, could you judge whether a detection passes? A raw detector often spits out 5, 10, even 20 slightly different boxes for the same object. Non-maximum suppression fixes that. The algorithm: take the box with the highest confidence score, keep it, and throw away any other box whose IOU with it exceeds a threshold. Then repeat with the next best box. The result: a single clean box per object. Without NMS, your prediction endpoint looks like chaos. In PyTorch, it's one call: torchvision.ops.nms. Pass in your boxes and scores, set the IOU threshold to 0.5, and you get back the indices of the boxes to keep. That's it. No custom loops, no manual overlap checks. Here's the trap with NMS. If you crank the threshold way down, 2 genuinely different objects that are close can get merged into one. Set it too high, and you'll see multiple boxes still clinging to the same object. A typical starting IOU threshold is 0.5, but you'll need to test with your own data. And always eyeball a few examples. A metric alone won't catch a merged rib crossing or a duplicated lesion. Transfer learning means you repurpose a model already trained on a colossal dataset. Here, ImageNet, instead of starting from random weights. The backbone already understands edges, textures, and basic shapes. You bolt on a new detection head, then fine-tune both with your own small dataset, perhaps 50 lung scans, to adapt the model. This slashes the amount of data you need and dramatically speeds up convergence. Even if you pick the general domain in custom vision rather than a specialized one, you're still standing on the shoulders of that pre-trained giant. When you have only a handful of scans, your model hasn't seen enough variety to generalize. Augmentation artificially creates realistic variations, slight rotations, brightness shifts, and horizontal flips, to teach the detector that a nodule rotated 3 degrees left is still the same nodule. For medical images, certain augmentations like horizontal flips can distort anatomical relationships. Always validate with a domain expert that your transforms don't alter clinical meaning. But flipping a clock face, for example, could destroy its semantic meaning. Always sanity check your transforms against your domain. Pause for a quick recall check. Why would you use data augmentation when training an object detector with limited labeled images? Pause and think. Data augmentation artificially expands your training set by applying transformations like rotation, cropping, and flipping, so the model becomes more robust to the variations it will see in the real world. This 6-step pipeline aligns with the computer vision domain often assessed on the AI 102. You'll create a project, feed it tagged images, kick off a training run, check the metrics, lock in the iteration by publishing it, then finally fire images at the prediction endpoint. Always with retry handling. Bookmark this list. It's the backbone of the computer vision domain. Code is powerful, but seeing the portal first crystallizes the domain options. Here, I'm logging into customvision.ai. I click New Project, name it Lung Nodule Detector, pick Object Detection, then the crucial dropdown, General, Compact, which influences whether you can export the model to certain edge devices later. One click later, and my empty project is ready for data. Exam pitfall. Many candidates mix up training and prediction resource roles, and that single mistake can cost you a domain question. So let's get it right from the start. You should create distinct resources for training and prediction. The prediction endpoint only needs read access to the model. Use the free tier, F0, if available, but always check current Azure documentation for supported SKUs. Notice the distinct kind parameters. That's what enforces the separation. One exam question that trips up even seasoned devs. How do you securely authenticate a custom module to Azure Cognitive Services? The trap answer is to pass an API key in code. The correct one, use a managed identity. A managed identity is an automatically rotated service principal in Microsoft Entra ID. No static secrets. Bind a managed identity to your compute, assign the appropriate RBAC role, check the current docs for the exact role name, and you're good. No credentials to scavenge from logs. For local development, default Azure credential with A's login provides the same keyless experience using your developer identity. Transient network errors happen in production. Without retry logic, you could lose tagged images and corrupt your training dataset. This script packs images into a batch, The size shown here is just an example. Check the latest Azure API docs for the maximum allowed, and wraps each batch upload with a few retry attempts using exponential backoff. Notice it also logs which images failed, so you never silently miss data. This is the difference between a toy script and production-ready code. Time for a quick recall check. After training and evaluating a custom vision iteration, what's the final step to make it accessible for predictions? Pause and think. Quick recall. What's the name of Azure's no-code tool for training custom object detection models? Pause and think. This isn't just tech debt, it's a back-office tax that bleeds real money. Consider a healthcare provider processing thousands of insurance forms. Their generic OCR system made so many errors that staff had to manually re-enter fields on a large portion of documents every month. When they switched to a custom-trained Azure Document Intelligence model tailored to their forms, error rates plummeted, saving the hospital significant money each year in manual rework. The lesson: generic OCR fails expensively on domain-specific documents. Custom training pays for itself fast. Now to train a custom document intelligence model. Using the Python SDK, you create a document model administration client with default Azure credential for keyless access, then call begin build document model with the neural build mode and your training data URL. The resulting poller gives you a trained model. A common pitfall: training can fail if images are too low resolution or poorly scanned. Always verify scan quality before kicking off training. Now let's extract actual fields. The document analysis client can be initialized with default Azure credential for keyless authentication. This removes hard-coded API keys, but double-check the current SDK documentation for setup requirements. You feed it a PDF, call begin, analyze the document with the pre-built invoice model, and iterate over the fields. Each field includes a confidence score. If it's low, route that document to a human review queue instead of accepting a potentially wrong value. For custom models, swap pre-built invoice with your own model ID. Everything else stays the same. Character error rate, or CER, measures how many edit operations are needed to turn an OCR output into the ground truth. It counts substitutions, insertions, and deletions, then divides by the total number of characters in the reference text. A lower CER means the OCR is more faithful. For example, a CER of 0.03 means only 3% of characters are off. Great for invoices, but a CER of 0.25 would spell disaster in a production pipeline. Let's make sure the intersection over union metric is crystal clear. Pause and calculate. Uploading and indexing a video programmatically is a single REST call. This PowerShell snippet sets your account ID, region, and access token, then posts a JSON body with the video URL and a descriptive name. If your video isn't hosted publicly, use a multi-part upload with the infile parameter instead. The key detail: once that call succeeds, Video Indexer begins processing your video, extracting insights like speech-to-text, object detection, and OCR, depending on your chosen indexing preset. You don't need to orchestrate separate pipelines. After indexing, retrieve insights with a GET request. You can include transcripts using the appropriate query parameter. Check the current API docs. Then filter labels by confidence to cut through the noise. You might keep only those above 0.7, for example. This gives you a clean feed of what was said and what was seen, ready for your downstream application or search index. But here's a feature few people talk about: Video Indexer's powerful search functionality. After you index a library of training videos, you can instantly find every clip where someone mentions safety protocol. No manual tagging required. Combine that with the pre-built widget SDK, and you can embed a fully interactive player with transcript and clickable insights right in your web app. For the AI 102, understand the key difference. Trial accounts have limited capacity. Paid accounts offer higher quotas and additional features. Check the current pricing page for details. If an exam question asks about a production video library, you know the answer. Choose paid. Let's recap the 3 pillars of production vision you built today. First, custom object detection. You trained a model with Azure Custom Vision, using data augmentation and transfer learning to catch what generic APIs miss. Second, document extraction. You used OCR and the Azure Read API to pull text and fields from receipts, invoices, and scans. Third, video intelligence. Azure Video Indexer gave you transcripts, face detection, and label analysis for video. Now, a quick knowledge check on fundamentals. In object detection, what 2 subtasks must a model perform that make it different from simple image classification? The answer: object localization, giving you the bounding box where, and object classification, giving you the label what. Those are the foundations of every production-grade vision pipeline, from defect detection on a factory floor to Azure's Read API for OCR.